Everyone, my topic is wireless power transfer in quantum radio and multi-carrier communication. My name is Xin Liu from Dalian University of Technology. My topic includes the 5 parts. The background for WPT, WPT for quantum radio, WPT for FDM, WPT for GFDM, and finally we will give the conclusions. WPT, that is wireless power transfer. Wires are fluid over leaves, and the intricate connecting with bring a lot of inconvenience. And also, the mobility of electrical equipment is great limited. But use WPT, we can harvest the energy from anywhere without any wires, and also we can get high mobility via WPT. In the traditional wireless power transfer, the energy source is very unstable and the energy density is very low. Also, we need large converters, and the conversion efficiency is not high. For example, when we harvest the solar energy or the wind energy, we can only get little part of them. The third is that energy equipment cannot be moved freely. In the wind harvest or the solar harvest, we must fix a large equipment in a specific area to harvest the energy. So these combinations have greatly limited the WPT. Wireless power transfer. WPT is the transmission of electrical energy from a power source to an electrical load, such as an electrical power grid or appliance, without the use of conductors like wires or cables. That is, using WPT we can harvest the electrical energy without any wires, and we can harvest the energy from anywhere in the room. So it is very convenient. The advantages of WPT has much. The first one is convenience. There is no need to replace batteries, because a common system it can harvest the energy from the surrounding signal resources, and this energy can use for its battery. So we need to replace batteries for the system. The second is that cost effective, because wireless energy is everywhere and it's ubiquitous and exhaustible, so it is very cheap. The third is environment protection. We all know that battery will pollute the environment, but use WPT we need the batteries and we will avoid discarding batteries. The WPT includes 2 kinds. The first is near-field WPT. Currently, our iPhone, our handphone, that with the function of wireless chargeable, they all use near-field WPT. That is, we take the phone near the wireless WPT sources, and it can harvest the energy. Another is the far-field WPT. Far-field WPT means that the batteries and the distance between the batteries and the signal source is very, very far. So the power is transferred by beams of electromagnetic radiation, like the microwaves or laser beams. This technique can transport energy longer distance, but must be aimed at the receiver. So near-field WPT may have better energy harvest efficiency, but the far-field WPT may have a low energy efficiency. But far-field WPT can allow the harvest equipment to be mobility. From this, we can see that there is many ways for the WPT, such as inductive coupling, magnetic resonant coupling, and EM radiation. From this figure, we can get that the inductive coupling may have the highest efficiency, but its harvesting energy distance may be low, maybe very short. And the magnetic resonant coupling, it will have higher efficiency but lower than the inductive coupling, but his harvest distance is longer than the inductive coupling. The electromagnetic radiation has the largest harvesting distance, but it may be have the lowest harvesting efficiency. Here we will introduce WPT circuit. WPT system consists of a radio frequency microwave generator and transmit antennas on the base station set. We also need a RF to DC convergence piece of the system consists of one or many receive antennas, matching networks, receiving circuits, and low-pass filters. That is, the radio frequency energy will be changed to the DC energy and stored in the battery by the rectifier circuit. Therefore, rectifying circuit is the core of the system. But when harvest energy, much energy may be radiated to the environment in the circuit, so the harvest efficiency of the system may be lower. The famous application for WPT is the satellite solar power stations. The satellite solar power station can convert sunlight to microwaves outside the atmosphere, and then the microwaves will be transmitted to the ground from the space. We know that it is a long distance, so the transmitting antennas must have good direction. The conversion of microwave power to DC power at the ground station will be performed by the receiving antennas. The sunlight will be stored by the ground station using the WPT, and it can be seen as a satellite solar power station. The rectifying antenna must have better energy harvest performance, so as to avoid much energy losses. We know that a radio frequency signal transmitted by a communication system may have both the information and energy on the signals. So the traditional WPT may only harvest the energy of the radio frequency signals, but the Swift can both get the information and the energy from the radio frequency signals. So we propose the Swift. Swift can provide energy for various devices while interacting with various devices. That is, the receiver can get the energy from the received signal while decoding or getting its information. That is, the receiver may have both the function of receiving signal and receiving energy. And the harvested energy will be used for the energy consumption of the information exchange circuit and the energy harvested circuit of the various devices. Core radio has recently been proposed to improve the spectrum utilization. It allows the second user to dynamically access the idle spectrum unused by the prime user, providing that the second user will not disturb the normal communication of the prime user. However, different from the traditional system, the second user must detect whether the PU exists in the frequency spectrum, depending on spectrum sensing. However, the spectrum sensing may consume much energy, and only the absence of the PU is detected. The SU can access the spectrum. So compared to the traditional system, the Cochrane radio must waste much energy for the spectrum sensing. That is, the energy stored in the battery for its data transmission will be decreased greatly, resulting in the decrease of the CR's communications. So, in core radio, the most important thing is that the spectrum sensing has depleted much energy, and we must try to decrease the spectrum sensing energy consumption and improve the transmission power. So we first propose simultaneous values spectrum sensing and power transfer, which is simply called SWSSPT. In the SWSSPT, the PU's energy can be harvested simultaneously while sensing the PU. We have two models. One is the time switch model, another possible model. In the time switch model, the CR receiver can perform as a spectrum sensing detector or energy harvesting equipment at any time. In the possible model, the PU's energy is divided into two streams. One stream for spectrum sensing and another stream for energy harvesting. So both the two models can perform spectrum sensing and energy harvesting simultaneously. In the time switch model, the frame structure of the CR is divided into three time slots: the sensing slot, harvesting slot, and the transmitting slot. And when the presence of the PU is detected in the sensing slot, the PU's energy can be harvested in the harvest slot. The harvested energy we can get as ETH, and also we can get the spectrum access probability of the second user as PACC. So our goal is to maximize the spectrum access probability by joint optimizing the sensing slot length and the time division factor rule. That is, the constraints have the four constraints. One is the detection property must set for our demands, and the harvest energy must satisfy the energy consumption of spectrum sensing. So we have proven the optimal problem is a convex problem, and it can be solved by the Lagrange-Doughty algorithm. In the possible model, the received signals is split into two streams, one for spectrum sensing and the other for energy harvesting. Then we can get the harvesting signal power and the sensing signal power by eigen rho p and rho p respectively. Then we can get the highest energy. And we also listed the similar optimization problem to maximize the spectrum access probability. These two simulations respectively show the optimal spectral access probability with same time and max spectral access with half the energy. We can see that these are sensing time. There is an optimal sensing time to maximize the spectrum access probability, and also the spectrum access probability will decrease with the increase of the harvest energy. That is, you harvest more energy, you will have less spectrum access. So we must get a trade-off between the spectrum access and the energy harvesting. Here we also propose WT in cooperative smart sensing. We also know that cooperative smart sensing is important for the current radio. In the cooperative smart sensing, many cognitive radio users to sense the PU, and a control sensor will receive all the local sensing results from the cognitive radio nodes and make final decisions on the presence of PU by fusing all the local sensing results. So it may achieve better performance if the CR node, if the channel from CR node and the PU is infected. But cooperative smart sensing also consumes more energy. In practical, not all the nodes participating in the cooperative smart sensing will have better performance because the cooperative overhead will increase with the increase of the number of the sensing nodes. So we can get the conclusion that only part of the nodes participating in the cooperative sensing will get the better performance. So if only some nodes participate in the cooperative sensing and the left nodes can be used for energy harvesting. So we also get the frame. The frame is divided in the sensing and harvesting slots and the data transfer slots. In the sensing and harvest slots, some nodes sense the PU and the other nodes harvest the energy of the PU. So we can see that there is an optimal number of CR users to maximize the transmit rate. The figure also gives the energy efficiency with the spare sensing time. We can see that the energy harvesting CS will achieve larger energy efficiency when the sensing time increases. But the transition model will not get the increase of energy efficiency with the sensing time. The TransitionSwift many have the following form models. One is a separated receiver. That is, one receiver is energy harvesting and another receiver is information decoding. The second is a time switch receiver. We have said above that the time is divided into two parts, into two slots. One slot is for energy harvesting and the other slot is for information decoding. The third is a pole splitting receiver. That is, the received pole is divided into two streams. One stream for energy harvesting and another stream for information decoding. Another is a antenna switching receiver. That is, it is a multi-antenna system. Some of the antennas is used for information decoding and another, the rest is used for energy harvesting. We all see that both all of the Swift model that we need a allocator. The allocator may be time allocator, power allocator, or antenna allocator. So this may increase the complexity of the receiver design. Here we propose a WPT for OIDM. In the new model, we needn't allocator. We just use some carrier for energy harvesting and the other carrier for information decoding. So the receiver utilizes different sub-carrier to harvest energy and decode information. We only need to know the sub-carrier index, but no splitter is needed at the receiver. We can get the achieved transmit rate from the transmitter to the receiver as this formula, and we also can get the harvest energy. Then we will list the optimization problem. We try to maximize harvest energy by joint optimizing the sub-carrier set and the power allocation. Then we can get the optimal power and optimal sub-carrier set to maximize the energy harvesting. To solve the problem, we list the Lagrange function, and then the optimal resource allocation is obtained through the following two steps. The first is obtaining the optimal power for a fixed substrate set G, and the second is obtaining the optimal substrate set G with a fixed power. From these simulation figures, we can see that the proposed OIDM sub-carrier allocation-based Swift significantly outperforms the other two algorithms. Here, we propose WPT for OIDM AF relay. We all know that cooperative communication system is very used in 5G because it can improve the transmission performance when the channel between the source and the destination is in series fighting. But the relay must forward the source signal to the destination, which will consume much energy. So in this model, we assume that the source signal have two paths. Some carrier is carrier information, and the left subcarrier from the source only carry the point. So the relay, that is accident, can harvest the energy of the source node while decoding the information of the source. And in the second phase, the relay will re-forward the source information to the destination by some carriers. Also, the left subcarrier will be used by the source node to transmit his information to the destination. So, the destination may have two kind of received informations. One is from the source node in the second phase, and another is from the forwarding of the relay. So, in this model, the relay helps to improve the transmission performance without less energy sacrifice. Here we can get the achieved rate and also get the harvest energy at the relay. Then we will list the optimization problems. The problems is that maximize the transmit rate from the source to the destination by joint optimizing the sub-carrier sets. and the pole, and also the subscriber pair. So we also list some constraints. One is the pole constraints, another is the harvest pole constraints, and the third is that the harvest pole must above the consumed pole. So we list the two simulation figures. One is the pole and subscriber allocation in first transmit phase, and the second is the pole and subscriber allocation in second transmit phase. We can see that some of the pole in the first phase will be forwarded in the second phase, but the subcarrier allocation in the two sets is different. That is because the subcarrier channel gains in the first phase and in the second phase are different. These two figures show the achievable rate versus some transmitter pole and the pole subcarrier allocation radio versus some transmitter pole. It is can see that the proposed algorithm will achieve larger rate. Then we proposed WPT for OIDM DF relay. In the DF relay, the source node is received by the relay, and the relay will decode the source signal and reconstruct the transmitted signal and translate it to the destination. So some creator is used for information decoding, and the left is used for energy harvesting. And in the second, the relay may use the harvest energy to forward the source signal to the destination, and also the relay helps improve the transmission performance with less energy accuracy. So we also can obtain the achieved transmit rate from source to the relay, and we also get the harvest energy at the relay from the source. Also, we can get the achieved transmission rate from relay to the destinations. Then we will get the transmission rate of source to destination. It is the minimum value of the source to the destination, and the rate from the relay to the destination. It is the minimum value of the two rates. So we can get the optimization problems, that is, maximize the achievable rate by jointly optimizing the subcarrier set and the pole allocations. So we also get two constraints. The one is that the harvest energy must above the energy consumption, and the second is that the total power must be lower than the maximum power of the source. So we can get two simulation figures. One is the achievable rate with transition pole. We can see that the rate may increase with the increase of the pole. And another is the pole and subcarrier allocation in first transmit phase. We can see that much of the subcarriers is used for information decoding, and only a little is used for energy harvesting. Then we propose the WPT for GFDM. GFDM is called as Generalized Frequency Division Multiplexing. It is based on the OIDM, but it has better performance than the OIDM because it can change his symbol according to the channel state in different time slots. So the GFDM can be seen as a multi-symbols transmit systems. It adopts two-dimensional data blocks defined in both time and frequency domains. The mapped data vector of the QM considers for k multiplies m elements, where k is the number of subsequent and m is the number of subsymbols. Here we consider a Swift schema for Downlink JFDM system with one access point and n users. The response of each user is divided into two streams by the possibility. One is for information decoding and another is for energy harvesting. So we can get the achieved information rate of each subblock, and we also can get the harvest energy of each user. Then we formulate the optimization problems. It is that we maximize the achieved rate of all the users. We also get some constraints. The first is that the harvest energy by each user must above its energy consumption. And the third is all the power of the users must be lower than the total power. So we can use KKT conditions to solve these problems. In the simulation figures, one is the sum of allocated power worth iterations. We can get the conclusion that after several iterations, we will get a stable allocated power. Another is the sum rate worth minimal harvest energies. We can see that the rate will be decreased with the increase of the harvest energy. That is, we must get a better trade-off between the rate and the energy harvesting performance. In this figure, we can see that the sum information declaration rate will be increased with the increase of the transmit power. That is, if we increase the transmit power, we will get more rate and more energy harvesting. Finally, we will give the conclusions. The WPT enables the receiver to collect radio frequency energy freely from the surrounding signal sources. We are converting the radio frequency energy to DC energy by an energy harvesting circuit. WPT4CR can harvest the radio frequency energy from the PU signal while sensing the PU, which can compensate the energy consumption of spatial sensing. WPT4OIDM can realize Swift by subcarrier allocation without installing any distributor, avoiding time synchronization of the time switching model and SR decreasing of the power splitting model. Then WPT4GFDM can improve the Swift performance due to that the two-dimensional data blocks make the resource allocation at a high granularity in time and frequency domains. Okay, thank you. Thank you for that. My topic is ever.